Hey, everybody. So here we are. We get to apply the information that we learned from the late, great Bob. No, wait. He's not dead. He actually lives up in northern Maine, and he runs a campground where you can rent out a yurt. Look it up. Anyways, today we're going to apply the concepts that he demonstrated in the shotgun demo, in the Newton's ball drop apparatus that we also saw, and solve things mathematically. At first glance, it may seem that there's too much information given in some of these problems. But in fact, if we follow a process, they're just as easy as everything else we've done. So what I would like to do is to go through the two examples on this sheet, front and back, titled Trajectory Examples. See, it's right in front of you. If you don't have it out, push pause and get it. If you do, get your calculator out so that I can see it. And let's get to work. So let's just dive right in. This says, a green bowling ball is rolled across the stage in the cafeteria. Don't ask. It's old school. It has a constant velocity of 2 meters per second across the stage. If the stage is 1.5 meters tall, how far from the edge of the stage will the ball land? All right. So your first approach in something like this is going to be to draw a picture. Always, your first step is to draw a picture. So I'm going to go ahead and do that. We're going to have a green bowling ball roll off the edge. This would be maybe, say, in North Hampton, I believe, they still have a stage in their gymnasium. We have a velocity in the x direction. And if it's traveling at 2 meters per second across the tabletop, that is going to be the velocity in the x direction. It says that the stage is 1.5 meters tall. And the question is asking, how far from the edge of the stage will the ball land? Now that value is going to be the displacement in the x direction. Now my question to you is, what does the path of that look like? Yeah, show me with your hands. Go ahead. Good. All right, yeah. Most of you said parabolic. Nice job. And it hits down there. Now, as Bob Crowley indicated, the time that the ball is in the air for, or the rock or the bullet, when fired horizontally, is only going to depend on the y direction. Before we continue with this math problem, let's go to a quick video that I shot in front of the room, your room, hopefully someday, where we can see that ball rolling and the path that it takes. Go to the clip. Oh, good one. Good. All right. Now that you saw a visual of something that you already could quite easily imagine, let's get on with the problem. So, in our detailed picture, there's one last thing that is missing. Yeah, you're right. I did not declare which direction was positive. But what I'm going to do is I'm actually going to make two directions positive. I'm going to make both right and down the positive directions. Okay, so my next step is to divide our information up into an XY chart. So let's do that. Now, this part seems easy, but there's some important points here, so listen up. In the X and Y directions, let's talk about a couple things. In the X direction, does the velocity change? No, it doesn't. In the X direction, the velocity is constant. Okay, good. If the velocity is constant, what's the acceleration? Yeah, the acceleration is going to be 0. Duh, because it's moving at a constant velocity. The distance in the x direction, that's what we're going to try to find. And the time it's in the air for? Yeah, we don't know that yet, do we? So let's take a look at what we know in the y direction. In the y direction, what is the initial velocity of the ball right when it leaves the edge of the table? Yeah, that's correct. Good. It's going to be 0. Now, that is the case because it is going off completely horizontally. It's not moving up or down yet. It will, but not yet. The final velocity in the y direction, that actually is talking about this component of the velocity the moment before it hits the ground. Do we know that? No. And the y component has nothing to do with the x velocity of 2. That does not belong there. So that velocity, we do not know. Displacement in the y direction is going to be positive 1.5 meters. Acceleration in the y direction is going to be positive 9.8. And now I have 3 pieces of information. I can solve that up and find the time. Now, what formula would allow me to solve for the time in this case? Yeah, that's right. Good. So I'm going to just do my work right under here. I'm going to solve for that time, t. So the formula would be d equals v naught t plus 1/2 at squared. I would utilize the formula that does not have v in it. V naught is 0. So 0 times anything is 0. So my formula is cleaning up here. And come on, pen. Sorry, just a moment. I'm going to solve this up. So I get d equals 1/2 at squared. Let's multiply both sides by 2. Divide by a and take the square root. At this point, I'm going to show my numbers plugged in. 2 times 1.5 divided by 9.8. Take the square root. And what do you get for the time? Plug it in. Practice. Did you get 0.618? Good, because the answer is 0.553 seconds. 0.553. So that means the ball is in the air for 0.553 seconds. So the question is, how far does it get to travel in the x direction during that time? So I'm going to take that value and write it in right here, 0.553 seconds. Now, in the x direction, because the acceleration is 0, it's very easy to find dx. I can go to my simplest formula, which is the average velocity is distance over time. Or if I rewrite this, distance in the x direction is velocity in the x direction times the change in time. See that? I just did a little algebra there. Okay, so let's get our numbers. I have 2 times 0.553. And what I end up with for an answer is dx is going to be 1.11 meters, if I recall correctly. What do you think? You got it? Yeah, I make it look easy. You know why? Because it is. It is for people of your caliber. You got this. Just to make sure we're all good. The steps. First step, draw a picture. Number 2, make a chart. Number 3, find the velocity in the x direction. Well, that was pretty easy. That was given. It won't always be. Find the time using the y direction was step 4. And then step 5 was finding the displacement in the x direction. What do you think? You got this? I think you do too. All right, cool. Nice. All right, look out the window. Take a deep breath. We're going to flip it over to the next side. Back side. Ready? Here we go. Oh, I already have some work shown. I'll edit this out later, hopefully. Let's give it a shot. And we're back. All right, on the back, example number 2. Why don't I read it out loud for you? It says, a young woman is being chased by a dog, a very large dog, Cujo-style dog. Up ahead, she sees the trail end and drops straight down to the ocean 30 meters below. That's over 90 feet. If she covers the last 40 meters in 8 seconds before jumping off the cliff, how far from the base of the cliff will she land? She had a choice. She could make this enormous dive off of this cliff and land in the water, or she could be eaten alive by a dog. Probably pull off your arm first, then go after a leg. So she jumped. I will say that when she jumped perfectly horizontally. Yep, she did. It's an impressive jump when being chased by a dog. So here's what I need you to do. I need you to draw this picture. Ready? Go. Now, you can just draw a square to represent the dog and the person. You can keep this very basic. Mine appears to be being chased by a cow. It's okay. I do this because it helps me organize the information that's in the problem. So my first thing that I notice is that it says that the ocean is 30 meters below. So I'm going to go ahead and put that right in my diagram. It also says that she covers the last 40 meters up until the edge in a time of only 8 seconds. And then she jumps. How far from the base of the cliff will she land? Okay. The only thing missing from my diagram is what? Yeah, that's right. The positive arrow. So I'm going to go ahead and draw that in. And again, I'm going to make down and right positive. So all of my signs need to be coordinated with that. Okay, so let's tackle it. I'm going to show my work on the left side because I added another question to the right. But let's go ahead and make our XY chart. In the X direction, the velocity is going to be, oh wait, it didn't give it to us. Huh. Can I do the problem? Yeah, that's right. Nice call. It's 5. How'd you get that? Of course, that's right. Velocity in the X direction is just going to be distance divided by time. And if she traveled 40 meters in 8 seconds, the velocity in the X direction would be a simple 5 meters per second. Nice job. Good. You do see, though, that other students looking at this for the first time may not have noticed that. Now, if I know the velocity, I know that the acceleration is 0. I'm looking for distance, and I don't know the time either. But as Bob Crowley taught us, I can find the time using the Y direction. In the Y direction, the initial velocity that she leaves the cliff with in the Y direction is 0 because she's going off perfectly horizontally. Final velocity, I do not know yet. displacement plus 30 meters down. Acceleration plus 9.8 meters per second squared. And I'm looking for the time. Now, even though I'm feeling pretty confident, after all, for you guys, this is the second whole problem you've ever done with this. So obviously you get it. This is roughly the 30,000th time I've done a problem like this, and I'm still going to show my work. In order to find the time, I'm going to utilize the formula. Yeah, there we go. D equals V naught T plus 1/2 A T squared. And this V naught T term is still going away for us. That's nice. So 2D divided by A equals T. And then if I take the square root of both sides, it gives me T. So 2 times 30 divided by 9.8. Take the square root. Ooh, I think in the Ed puzzle, I'm not going to let you go on until you get this right. Good luck. Did you get 6.122? Well, that'd be wrong because you got to take the square root. I've got a time of 2.47 seconds. I'm sure that during that 2.47 seconds, she was really contemplating some of her life's choices. Just like I am while I'm doing this problem. So now, to find the distance it traveled, to find dx, I can just use the simplest formula out there. Distance is velocity times time. Now, just for kicks, watch. Look at the similarities. If I were to write down plus 1/2 AT squared, what's the acceleration in this case? Yeah, 0. See? Good. I'm going to erase that. Now, dx is then going to be equal to 5 times 2.47. So the displacement in the x direction that she travels while in the air is going to be around 12.4 meters. There it is. Good. Thanks for staying with me. Now, thought you were done. So the last thing to tackle here is, what is the velocity the moment before she strikes the water? Well, let's think about what the vectors would look like as she's flying through the air. This velocity in the x direction, that component is going to stay constant. So right here, halfway, I'm going to draw the same velocity in the x direction. And the moment before she strikes the water, it's going to be the same Vx. But you know as well as I do that as she's falling for all of that time, she's going to be going faster and faster in the y direction. So if I know Vx is 5, can I solve for Vy? Yeah, of course I can. Let's do it. So my first step to find the total velocity would be to find the velocity in the y direction first. So given that, let's look. In the y direction, I have V equals V naught plus AT. Oh, that's easy. It's even solved for the variable for us. 9.8 times 2.47. Yeah, she's going to be going 24, whoa, that's fast, 0.2 meters per second in the y direction when she strikes the water. So how do I take that and add it to the 5? Well, 5 plus 24.2 is going to be 29 point, right? Just add 5. But they're not in the same direction. I have to add them as a vector because the direction matters. This is a bit of foreshadowing. We'll do a lot with this. Relax. You got this. So if I have a velocity of only 5 in the x direction and 24.2 in the y, how the heck do I add those two things? Well, what I can do is sort of transform them so that I'm adding them tip to tail. And the resulting velocity will be this component. I'm sorry. The arrow that I just drew will be the actual velocity of the object. Now I can solve for that. Oh, x and y are perpendicular to each other. They make a right triangle. Because of that, I can use, I can use Pythagorean Theorem. So v squared equals 5 squared plus 24.2 squared. Take the square root. I got 24.7 meters per second. Good. Can I find the reference angle here? Yeah, of course I can. Yeah, right? To find theta, I could just use trig. And since I'm given the opposite and the adjacent side, I can ask my calculator, what angle of theta would give me a ratio of 24.2 to 5 for the opposite over the adjacent side? And you ask your calculator not in English, but by typing it in like this, and it spits back an answer to you of, oh, got to make sure you're in degrees. That helps. I got 78.3 degrees. Nice. But where's 78.3? What quadrant? Yeah, it's in the first quadrant, isn't it? And my answer's not in the first quadrant. Look at it. It's clearly pointing down. So in order to get the actual angle, if I look at my coordinate plane, and the angle down, the reference angle, 78 degrees, then what is the actual heading? Yeah, good for you guys, right? If you do 360 minus 78.3, that would give you the actual angle. Or 282 degrees. Okay, now that last part is really a couple lessons down the road, but I just couldn't help myself because I know that you guys can get it. And here's the thing, if you don't get it right now, relax. Your brain is going to work on it tonight while you're asleep. It is. You're going to have dreams about that angle right here. I want you to look closely at that. And you'll say, oh, now I get it. Or maybe you don't. Don't worry, I'm going to teach you again anyways. So what we went through were the trajectory examples. And while you had never seen something exactly like it at the beginning of the problem, by the end, it already seems like old hat. You got this. You got this. All right, thanks. Have a good rest of the day. Or whatever you're doing. I don't even know what time it is, whenever you are watching this in the future. Where's the music?